to meet Wojtek and exchange ideas, and we seem to have common interests. I made a contract to come here, and it was a contract under asymmetric information. You didn't know what you're going to see. And what is a contract? If you open the dictionary, a contract is a binding agreement. That's what the dictionary says. And this agreement could be either verbal or written. And typically we make those agreements because we give something, we exchange something, we get something in return. I give you something, you give me something. We want to write this down to make sure we keep our promises. It's very difficult to imagine any contracts that we made which are deterministic. Almost any contract that we make is uncertain, like the weather today. And the idea of contracts, exchanges, goes back to, let's see here how this works, to Aristotle. In his famous book, Ηθικά Nicomedia, Nicomedia Ethics, Aristotle introduced the term economy, and is based on two words, eco and nemo. Eco is a house in ancient Greek, and nemo means arrangements, distributions. Has many meanings, as a matter of fact. So economy means household arrangements. And Aristotle was so clear-minded. He developed the idea of exchange values, which was subsequently adopted by classical economists like Ricardo and Marx. And I'll tell you what it is. It's the labor theory of value, as it's called. In other words, if I produce something and I have spent time producing a good, I have invested in the production of a good, this good has some exchange value simply because labor is embodied in the production of that good. And any good, in other words, which has been produced by means of labor, has some exchange value. And of course, there are goods which are useful, very valuable, and have no exchange value. For example, the most valuable good that we all have, which is the same, is the air that we breathe, has no exchange value. Why? Because labor is not embodied in the production of the air that we breathe. It's abundant. And economists distinguish those two things, exchange values and value in use. Marx spent a lot of time on this, how to transform exchange values into prices, and classical economies, until the 1890s with the introduction of Walrasian's book and Pareto's ideas, the Neoclassical economics. It turns out that this labor theory of value doesn't work because what determines the price of a good in the market is not how much time we have spent for the production of a good, but how much we like something. A Rembrandt painting, 5 by 6 inches, fetched $10 million. Probably took him half an hour, 2 hours a day. And there are big mansions in outside Urbana-Champaign, which took years to produce those beautiful houses, and you buy them for next to nothing. So the labor theory of value cannot explain the formation of prices. And the transformation from exchange values to prices, which was the problem that Marx tried to tackle in order to show that there is a discrepancy, a contradiction between the rate of profit and exploitation, and the big contradiction. It did not really work, and you cannot really transform exchange values into prices in a logical way. So in modern now economics, we say an economy consists of individuals like all of us here, and each individual is characterized by her preferences and her initial endowments, initial resources. That's what we have. You have your initial resources, your possessions, and your preferences. And we engage in exchange of goods. And we try to see what's the outcome of the exchange of those goods, commodities that we trade. And commodities could be either actual goods or services. And rigorous economics actually was developed from the 30s to 60s, 70s, 80s by von Neumann, Aero, De Breu, Mackenzie, Nash, that you know, he was here a couple of years ago, I think, Aumann. And all these theories based on the Walrasian ideas, the ideas of Leon Walras, and the idea is very simple. Walras said that since agents are characterized by preferences and initial endowments, individuals, agents, or consumers if you like, will try to maximize their preferences or their utility functions or their payoffs. Those things are equivalent, subject to their budget constraint. That's what we typically do, right? We maximize our utility, our preference, our satisfaction, subject to our budget constraint. And Walras said that if everybody in the economy is trying to do what is selfish for herself, to maximize her own utility, satisfaction, subject to her own constraint, for the economy as a whole, we're going to reach an outcome where total demand is going to balance the total supply. And that's what we call Walrasian equilibrium, some people call a competitive equilibrium. And that was the focus until recently. And the two basic questions is that for the Walrasian equilibrium were the existence, under what conditions an equilibrium exists, and typically we prove it by means of a fixed point theorem, the Brouwer fixed point theorem or the Kakutani and KKM lemma, things like that are used to prove the existence of an equilibrium. And the second property of the equilibrium is the efficiency. We want to know as to whether or not the equilibrium is efficient, Pareto optimal as it's called, because the notion of efficiency was introduced by Pareto. What it means that we have reached an efficient outcome if it is not possible to make a redistribution of the resources and make some people better off. In other words, no further redistributions are possible. And for this, the book of here at Purdue, Professor Liprandis is the state of the art. It's the best book for this classical theory. This theory is deterministic, talks about trades, exchanges, contracts, and there is no uncertainty. But De Breu, and on a famous book actually, his thesis as a matter of fact, he said, let's go a step further. Let's assume that agents' preferences or utility functions or payoff functions and initial endowments, initial resources, are random. They depend on an exogenously given state space. We have a probability measure space which denotes the states of nature of the world. And our preferences now and our initial endowments are random. They depend on the states of nature of the world. And De Breu said the following thing. Let's say that in each state we make a trade, a contract. In other words, if it is sunny, we're going to go outside to play soccer. If it's going to rain, we're going to stay at home. We're going to stay home and watch a movie. But for each particular state, we're going to have a different contract. And when the state occurs, we're going to execute the contract. That's why this model is called the state contingent trade model. We make trades contingent on the realized state of nature. And De Breu noticed that all classical results, the existence and optimality of the Walrasian equilibrium continue to hold. Incidentally, the fact that the Walrasian equilibrium is optimal, it was a conjecture of Adam Smith of The Wealth of Nations. You remember the invisible hand. Adam Smith was saying that if you allow individuals in a society to pursue their self-interest, then by somehow invisible mechanism, the invisible hand, we're going to reach an outcome which is going to be the best possible outcome for the society. In other words, pursuing the self-interest still is going to lead to a nice outcome. And these economists, they did prove that conjecture actually rigorously, that if agents are allowed to maximize their utility subject to their budget constraint, for the economy as a whole, we're going to have balance of the resources and this outcome would be efficient. Let's come now to asymmetric information. We want to enrich this model because it does not represent the actual contracts that people make in an economy. Typically, agents make contracts based on their own information. You know things that I don't know, and I know things that you don't know. And we try to trade, to make exchanges, contracts. And information, as we're going to see, plays an important role in constructing contracts. And we have to incorporate this asymmetry of information into the model, not only because we're going to be more realistic, but we're going to understand better how contracts are written. Our goal is to construct good contracts. And by good contracts, we have to define what good contract means. Because, you know, to find bad outcomes, it's easy, really. What is difficult is to find ideal contracts or ideal situations, or even if they are not ideal, something which is close to ideal. I see now that I forgot to mention to you the idea of perfect competition, what perfect competition means. Competitive equilibrium is what I told you. But perfect competition means that no individual is going to be able to exercise any influence on the prices at which goods are either sold or bought. In other words, as individuals, we are price takers, and we cannot have any influence on the price of a good in the market. Yes?
Are you assuming that time is continuous?
At the moment, I haven't said anything about time. That's a good question. At the moment, you can say it's a static model, and you can say that trades are taking place instantaneously, fractions of seconds. But later, we can make it dynamic, and we can involve time, and we'll see what happens.
I'm just wondering, because you could have a cobwebbing effect. If transactions occur only over certain seasons, and prices are low, so no one produces much, so then the supply.
Yeah, we don't talk about the dynamics at the moment. The questions are very, very basic. What is a good contract, what contract means, and then we can go to the dynamics. Those are interesting questions to talk about stability, you're going to see later on, and convergence to good outcomes, etc. We're going to go into this. And the idea of perfect competition actually is very important, and Aumann, that was the contribution of Aumann actually on perfect competition, because the classical economies had adopted a finite agent economy, and they were talking about perfect competition. And Aumann said that as long as you have finitely many agents, each individual has an effect. Therefore, we cannot talk about perfect competition. We can talk about an equilibrium, but this equilibrium may not be perfectly competitive because an individual may have some effect at the price at which a good is either bought or sold. And he formalized the idea of perfect competition by having a continuum of agents. As a matter of fact, strictly speaking, mathematically speaking, an anatomic measure space of agents. And in this case, each individual has exactly measure 0, is exactly negligible, and as a result of her negligibility, we take price as given. Of course, this is the ideal model, but the world is finite, it's not infinite, but we have results where we approximate infinite economies, continuum economies by large but finite economies. So in other words, those ideal economies could provide intuition, could provide results for large but finite. And that was the contribution of Aumann. I mentioned to you what is perfect competition because I want to come back later on at that point. A few economies, and this is work from 70s and 80s and even 90s, and people still use the concepts of Walrasian expectancy equilibrium, where I'm going to tell you what it means, rational expectancy equilibrium, and those are the people Lucas Radner, Prescott, that they talk about those notions. We have now an exogenously given probability measure space, which denotes the states of nature of the world. And we want to enrich the economy. What we want to do is to introduce asymmetric information. We're going to assume that preferences and initial endowments now depend on the stage of nature of the world. They are random. But also we're going to assume that each individual has her own private information. The private information now is modeled as a partition of the underlying exogenously given measure space. What is a partition? You remember is pairwise disjoint events whose union makes the whole state space. And our partitions are different. So I may be able to distinguish some events, you may not be able. And typically, on the things that I'm able to distinguish, on the information that I'm able to distinguish, I should be able to make beneficial trades. And in principle, if there are two agents who make contracts, the better informed person should typically get more because it has advantageous private information, so to speak. Therefore, would have an information advantage, and as a consequence, her payoff should be larger. But let's think now, incidentally, let me tell you up front that those concepts do not seem to work properly, and I'm going to tell you why. What is a good contract? Or what is, you and I write a contract, or you write a contract. What would you like? Why, first of all, do you ever write a contract? Well, you make contracts to become better off. You don't make contracts with anybody that you think you're going to become worse off. If I come to you and I'm telling you, let's trade something, and you think that I don't have anything to offer to you, you say, go away. So you only make contracts to become better off. Better off now in terms of expected utility, because typically we make contracts before the state of nature is realized. Like with me here, we made a contract, I'll come here. I didn't know anything about the players, you didn't know much about me either. And that's the way we make contracts. We make contracts ex ante, before the state of nature is realized. Sometimes we make contracts in an interim stage where there is some signaling, and I'll tell you what I mean with this. But the only reason we make the contract is for both parties to become better off. So that's what we're going to call individual rationality. Individual rationality, mathematically speaking, it means that your expected utility at your resulting contract should be at least as high as the utility that you obtain from your initial resources. In other words, trade is going to make you better off. You would like your contract to be efficient. Imagine you make a contract with somebody else. If it is inefficient, this means that both of you could have become better off, or you could have become better off. You made a mistake. So you go back home and say, oh, I made a mistake, I have to recontract. But once you sign the contract, it's binding, as we said, it's a binding agreement. So one has to be careful. Once you make the contract, the binding agreement better be efficient, because otherwise you have to go back and renegotiate. And renegotiation is not so easy because you sign a contract. So it has to be efficient. What else? Incentive compatibility. That's the key, and that's where the information plays an important role, and that's actually fundamental here. What incentive compatibility means? Incentive compatibility means that if you and I try to sign a contract, I should not be able to cheat you in states you cannot distinguish. Imagine you're blind and it's raining outside, and I'm telling you it's sunny. Because this way, I don't have to take you outside. Because I don't want to go out, and I lie to you, you cannot hear. So all I want to say is that if there are states that I can distinguish and you cannot, I shouldn't be able to misrepresent my information and benefit. And as you understand, that's what happens all the time. People distort information because it's advantageous to them. So I want to stick to that incentive compatibility because it's very important. Existence is also a fundamental issue here, because once you have a contract, you sign a contract which is individually rational, efficient, and incentive compatible. You also want to know that there are reasonable assumptions, conditions under which this contract exists, because if it does not exist, or if the assumptions are so extreme, maybe that's not a good contract. So existence is a fundamental issue. And as a matter of fact, in all this literature, the existence is the most difficult issue mathematically to prove, and is always based on some kind of a fixed point argument. The fifth one now, it's something which is quite interesting and intellectually very stimulating. Implementable as a perfect Bayesian equilibrium of an extensive form graph. What does this mean? This has a flavor of the dynamics. The contracts, the way we're going to analyze them here, would be by means of some kind of optimization method, a fixed point, say. That's a solution of the contract. And I'm going to ask the following question. Is it possible to construct an extensive form graph, or game tree if you like, and show that if players, individuals, consumers, act in terms of their best replies, best reaction function in terms of Cournot and Nash, then this contract is consistent with the idea of perfect Bayesian equilibrium. In other words, a contract that I found by solving an optimization problem, I can now map it into an extensive form graph, see the dynamics, how from each node move to another node, the moves, the sequential decision making of the individuals, and to see as to whether or not my contract is implementable as a perfect Bayesian equilibrium of an extensive form game tree. So in other words, this static problem that we see that we solve, I make it dynamic in terms of the game tree, and I see how people sequentially played and reached that outcome. And it turns out that equilibrium notions which are essentially compatible are consistent with Bayesian rationality, with this one. Equilibrium notions which are not essentially compatible violate 5. One more important issue here is the following, that perfect Bayesian equilibrium is playing kind of Cournot-Nash strategies from each node of the game tree, and there is some consistency there in terms of beliefs. But the concept of a Cournot-Nash equilibrium is non-cooperative. And some of the contracts that we are writing are cooperative, have been written by means of cooperation. So this 5 is consistent with Nash's idea. You remember when Nash introduced the idea of non-cooperative equilibrium, he said, well, this idea is not interesting from an economist viewpoint because it's not efficient. However, may be of interest because we can provide non-cooperative foundations to cooperative outcomes. In other words, we reach cooperation by means of non-cooperation. And that's typically the case. You bargain, you play non-cooperatively until parties understand that by cooperation they could become better off. So this 5, because we're going to implement cooperative solution concepts, goes beyond the Nash program in the following sense, that not only it provides non-cooperative foundations to cooperative solution concepts, but also we see the dynamics. And this is very important analytically. Okay. Let me tell you something which is very interesting. It turns out that the Walrasian expectancy equilibrium and rational expectancy equilibrium violate all this from 2 to 5. So the rational expectancy equilibrium, as you know, may not exist, need not be efficient, need not be incentive compatible, need not be implementable as a perfect Bayesian equilibrium. There are counterexamples. Okay. And we'll have to go beyond that. It seems to me that in order to find good outcomes, you have first to put down the objectives. What do you want from your equilibrium notion? And I may have missed something, I don't know. I was always thinking what's the best possible contract, and I thought if I have a contract which has all these properties, I'll be glad to have such a contract. If you think that there is something else that we need to add, I'm open to suggestions. Let me now tell you something which is very important. can we construct in a finite agent economy a contract which has all the above properties? The answer is no. You just cannot. This is a really nice contract that you want to have, but you cannot. And I'm going to give you counter examples. The best you can hope is that you can construct a second best optimal, second best efficient contract. By second best, I would mean something which is individually rational, is essentially compatible, it exists, it is consistent with implementation as a perfect Bayesian equilibrium, but is not fully efficient. It's less than fully. It's second best. You lose a little bit of efficiency, but you are guaranteed something there. Okay? That's the best you can hope. And I'm going to go into this. Now, can we construct an environment where first best obtains and all those fine conditions can be achieved? And the answer is yes, if you have perfect competition in an asymmetric information economy. It's very difficult to define perfect competition in an asymmetric information economy because the Almond model doesn't seem to work. You may have a continuum of negligible agents in terms of their initial endowments. But I may have just one person who is negligible in terms of her initial endowments, but her information is so fine that could make a Pareto improvement, a redistribution, and make everybody better off in the whole economy, in this continuum of agents. In other words, my information is so good. Imagine somebody who makes a technological innovation and makes the whole society, Maxwell, better off. There is a tremendous informational advantage there. Therefore, again, you cannot, even if you have a continuum of agents, you cannot talk about perfect competition unless you provide conditions which make the information of an individual negligible, infinitesimal. And therefore, you can talk about perfect competition. But what is negligible information? How do you model infinitesimal private information? Remember, private information is a partition. So this actually involves probability theory. And the last few years with a friend of mine, a mathematician from Singapore, who have been working on those problems, it turns out that you have two measure spaces. One is for the state space, the other one is for the agents. And Lebesgue measurability arguments do not work. There was a famous counterexample by Dubé since the 20s that there is a joint measurability problem. And you have to work with richer measure spaces to get around this. And it's possible. Towards the end, if we have time, I may mention something about this part. The book, Glycopandis Yannelis, has most of the issues that I already alluded to, and it's a good reference to have. Let's go into now the rigorous analysis of differential information economy. I'm going to give you definitions, and then I'm going to go into examples to understand what is happening. And I'll try to sum up towards the end. A differential information economy. So as you see, the state space, the random consumption set of each individual. We have the private information of each individual, is the partition as we said. A random utility function, pair function, a random initial endowment, and we're going to assume throughout that the random initial endowments are measurable with respect to our own information. Measurability with respect to our own information, it means that in states that I cannot distinguish, my initial endowment should be the same. That's what measurability means. In states I cannot distinguish, my initial endowment should be the same. Measurability is a very important condition, as you're going to see, and I want you to understand measurability, actually. I'm going to go over and over again on measurability, because it turns out measurability can characterize incentive compatibility. So, and I'm going to try to make this clear even in words. And each individual has a prior. It's a probability that you give for an event to occur, and each individual have different priors. And that's the way actually agents are characterized in an economy. Our random consumption set, our random preferences, our random initial endowments, our private information set, and our priors. That's all we have when we engage in exchange of goods and try to make a contract. Now, although as we said before the model is static, we're going to give a two-period interpretation as follows. We're going to assume that we make contracts ex ante before the state of nature is realized. We do not know what the state is going to be tomorrow, but we make contracts today. If we knew what the state is going to be, that would have been a complete information contract, but we don't, and typically we do not. But at this stage, in the ex ante stage, given the information we have, we try to make the best possible contract, and that's our goal. In the second period, tomorrow, the state is going to be realized and consumption is going to take place. That's why, because we don't know which state is going to occur, we calculate our happiness, our payoff in terms of our expect utility. And we integrate with respect to all possible states of nature. We have here finitely many states. And that's the ex ante. We also have the interim, and the interim means that you have a signal. You do know which is the event which contains the realized state of nature. And for a state which is on the event which contains the realized state of nature, you follow Bayes' rule. And for the state which is not in the event which contains the realized state of nature, you give zero probability, and you update your posteriors according to Bayes' rule. This is the interim expect utility. So you integrate with respect to the event which contains the realized state of nature, and the interim expect utility always depends on the realized state of nature. There is some signaling, like the signal tonight, we're going to get from 8 to 12 inches of snow. So, given this, I thought that I better leave before. Okay. Some notation, although we may not use it so extensively, it's good to remember. This becomes your consumption set, really. You get FI measurable selections out of your consumption set. That's your consumption set. And this set is not empty thanks to our policy competitors, Kuratowski and Ladrevsky. Once you have measurability properties here, there are always measurable selections, and this is non-empty. When I take the product, I have L sub x without the I. And this is the same set without the measurability. This is the same set without the measurability. Okay. So an allocation, a redistribution, is an element of this set, or sometimes of this set, depends if I have measurability or not. Okay. With this in mind now, I'm going to start with a very simple example. Is it possible for agents to write contracts which are efficient or Pareto optimal and incentive compatible and exist? Let's give a very simple example. There are two agents, agent 1 and agent 2. The utility function of the first agent is independent of omega, is square root of x1. There is just one good. And the utility function of the other person is again the same utility function, square root of x2. As a matter of fact, any kind of utility functions would work here. There are three states of nature, A, this should be B and C, I didn't see that actually. A, B, and C, A, B, and C, three states of nature. And each state occurs with the same probability, 1/3, 1/3, 1/3. Okay? Three states of nature. We do not know which state of nature, of course, is going to occur. But each one is going to occur with the same probability, 1/3, 1/3, 1/3. Now, the initial endowment. If state A occurs, this first guy is going to have 10 units of that good. If state B occurs, it's going to have 10, state C, 0. The other guy, 10, 0, and 10. And the private information The first guy cannot distinguish between A and B, and the other guy between A and C. And the first guy knows C, the other guy knows B. So as you see, their initial endowments are measurable with respect to their own private information. In the states they cannot distinguish, like AB, their initial endowment is the same. AC is the same. That's what measurability means. In the states you cannot distinguish, your initial endowment should be the same. Okay. Suppose I'm agent 1 and you're agent 2. If you're agent 2, do you care if A occurs or C occurs? No, you're going to get 10. You're perfectly happy. You cannot do better than that. The same with me if A or B occurs. But I do care if C occurs. I'm going to starve. You do care if B occurs. You're going to get 0. You're going to die. So how are you going to think now? You're going to come to me and you'll tell me, Nicholas, let's do the following thing. Why don't we divide this risk equally? And let's say that if C occurs, I'm going to give you half of my 10. If B occurs, you give me half of your 5. And that's the best possible contract we can write, right? We have diversified the risk, we have pooled the risk. It's perfect risk sharing now, right? Because we don't know which state is going to occur. We both want to live. You want to live if B occurs, and I want to live if C occurs. The only way to survive is to diversify our risk and to do perfect risk sharing. And that's the contract we can write. That's the best contract. However, this contract is not essentially compatible. And let's see why actually it's not essentially compatible. Suppose A is the realized state of nature. A. I'm in my event A, B. I don't know if it is A or B. And you don't know if it is A or C. You have 10, but you don't know if A has occurred or C has occurred. And let's assume that I'm a liar. I'm not. I came after all in bad weather conditions. And you think that Nicholas never lies. You think. Not true, of course. But I would lie now. I'll tell you, you're in your event AC, and I'm in my event AB, and I'm telling you, oh, you know, Wojtek, C occurs. And the contract we made was, if C occurs, you're going to give me 5, right? We're going to have 5, 5. And Wojtek thinks, oh, Nicholas is such a nice guy. He never lies. He's going to give me the 5. So I'm going to have the 10 because I'm in my event AB, I'm going to have a 10. I'm getting another 10 from Wojtek. I'm going to have 15. And I'm better off at the expense of Wojtek. Because remember, if somebody cheats, people only cheat to benefit. People, cheaters and liars, have only one objective, how to become better off. Otherwise, they don't cheat, right? So I became better off, and poor Wojtek lost half of his wealth by being truthful. This actually, I'm going to go back into this pretty soon. This example shows that's a contract which is fully Pareto optimal exists, but it's not essentially compatible. And if you write such a contract, you could lose half of your wealth. And people do this all the time, actually. Okay. So this is the counterexample which demonstrates that we just cannot write a contract which is essentially compatible, fully Pareto optimal, and also this contract exists. Those are really very good circumstances, and they indicate that such a contract is not possible. Okay. You have a question? Yeah.
You could make it incentive compatible. I know.
I can, and I'm going to show you how to make this essentially compatible. As a matter of fact, I can. And small parenthesis, the way to make it is and the correct way to sacrifice an efficiency, second best, okay, that's one. Another way to make it, and this I don't like, is to introduce a third party, court or an exogenous enforcer, which penalize the agents. But when you and I write a contract, to expect that the court is going to know exactly what happens. If you're in Urbana at 2 o'clock after midnight and we're both drunk and you hit each other, I'll claim that you were drunk, you claim I'm drunk, and there is nobody there, no eye. 2 o'clock after midnight, I guarantee you, nobody who have seen anything. You cannot expect now the court to know the truth. We're going to go into this. Actually, those are delicate issues, how to make a contract enforceable, actually. But in principle, the best idea is to sacrifice on efficiency a little bit and to guarantee that the contract is semi-compatible, because this is implementable. And I prefer those contracts because they're not fully Pareto optimal, they're second best, but they have all the other properties, so I'm happy enough with this. Okay. Did I change? No, did not change. Okay, here it is. What I just told you is written down, that when A occurs, I told you the C, I made a net trade, and I got a 15, the 5 you gave in state C. And if I tell the truth, I will have 10. Okay. So this example demonstrates that full or ex post Pareto optimality, efficiency, is not compatible with the semi-compatibility. As a matter of fact, we have resolved this problem in a perfectly competitive economy. It's a forthcoming paper in the Journal of Economic Theory this year. I'm going to now demonstrate the role of the private information measurability of an allocation. That's very important. This is of fundamental importance. Let's now have, again, 2 agents. And now I'm going to have 2 states, state A and state B. Each state occurs the same probability, 1/2, 1/2. And there are 2 goods, good X and good Y. If state A occurs, the first guy is going to have 10 and 0. From 10 from the first good, 0 from the second good, and 10, 0. And agent 2 is going to have in state A 10 units from the first good, 8 units from the second, and 0 and 10. As you see before trade, they have 0 happiness. And there's tremendous room for trade. And they will trade here. That's a good contract, right? Both became better off. Now, this 2 is for the payoffs, allocations. This contract that they made is fully Pareto optimal, ex ante, ex post. It's just beautiful contract in terms of efficiency. It turns out that this contract is not semi-compatible. Let me tell you why. Suppose that B is the realized state of nature. This guy doesn't know, cannot distinguish the A and B, right? You see, his initial and downs are the same in A and B, measurable with respect to his own private information. So, if B occurs, it's supposed to get 5 units from good X and 5 units from commodity Y. And this guy is supposed to get 5 and 5. But I can distinguish, and I can tell you, you know what? It's not state B, it's state A. You cannot distinguish if you're in state A or state B. Therefore, I'm going to give you 2 units of good Y instead of 5. And in this case, I'm going to end up with 8 units of good Y instead of 5. Right? So B occurs, you're supposed to get 5 and 5. You cannot tell if it's A or B. I'm telling you, oh, you know, it's state A. So I keep 3 units from you and I put them in my pocket. And you have no way of telling. So this contract is not semi-compatible. Now, this, can you see what the mistake that agent 1 made here? Can you see? He plays non-measurably. He cannot distinguish A and B, and he played like that. That was a mistake he made. It was a mistake. He should have played measurably. If he had played that way, you see? If he had played that way, had made that contract, 5, 5, 5, 5, this guy cannot cheat him. In either state or B, the outcome is the same. He made a logical mistake. He played non-measurable. Do you understand this point? Let me get, I don't have any coins. Do you have a coin? Just one. Yeah. Okay. I would flip the coin, And I'm going to ask you to make a bet with me. If it is head or tails, you pick the outcome. You're going to give me $1 on heads, and I give you $1 on tails, or vice versa. You pick the outcome you like. So I'm going to see the outcome. You're not going to. You're not. So your private information is you cannot distinguish between head and tails. That's your private information. And I can, because I'm here. Can you tell? You cannot tell, right? Now, if you make a contract with me, you're bound to lose your money. You know, of course, I don't lie, but I may lie to demonstrate to you that you made the wrong choice. You should not make a contract. And you have to play measurably. And measurably means that you don't make a bet, either head or tails, because you cannot see the outcome. Okay? So, and I have an incentive to. Okay. Let me now give you one more example, and I'm going to some definitions. Let's see what is that. Oh, that's a very interesting example too. Very interesting. Very interesting. This is very interesting because the whole literature, when I started working on this something like 15 years ago or so, there's a whole literature that people were talking about incentive compatibility. Started after 76, 78 or something, incentive compatibility, and formulated in terms of the Harsanyi model, which is not the appropriate model to talk about incentive compatibility, actually. We don't have the time to go into this, but on the book of Glycopantis Yannelis, you're going to see some of those issues. I'm going to have now a contract here, and I want to make the following point. There's a contract written by 3 individuals. There are 2 goods, X and Y, 3 states. Again, each state occurs the same probability. And as you see, agents 1 and 2, before any contract is written, they get 0 utility, okay, because of those zeros there. They are private information, consistent with their initial endowments. Now, we make a redistribution, you make a contract. And this contract is incentive compatible. As you notice, I can cheat somebody, or he can cheat somebody on the states the other person cannot distinguish. You cannot cheat a person in the states that can distinguish. You can cheat somebody in the states she cannot distinguish. Now, the only person who can cheat now, agents 2 and 3, is agent, this is supposed to be a 3, I'm sorry about that. The only person who can cheat here is agent 3, because if A occurs, he can tell this guy is B. This guy cannot tell, and to this guy can tell him B or C. But as you see here, if it is A or B, agent 3 has the same consumption, therefore has no incentive to lie if it is A to say that it's B. It doesn't benefit. So this contract is individual incentive compatible. No individual has an incentive to lie and benefit here. However, look what is true. Agents 2 and 3 can make a coalition, they can get together, and when C is the realized state of nature, and this guy is supposed to get 12.5 from good X and 7.5 from good Y, they can tell him that is state B or A, because this guy cannot tell if it is A, B, or C. So C occurs, this guy gets 2.5, 2.5, this guy gets 25, 25, but they tell this guy is B. So they give him 10 and 5, so they keep 2.5 units of good X and 2.5 units of good Y, and can they redistribute among themselves. So this contract is individually incentive compatible. No individual party has an incentive to lie, but the 2 of them have an incentive to lie to the 3rd person. This happens all the time. Especially if you build a house, always the contractor, subcontractors, sometimes include the architect, they cheat you. Go and figure out what they have done there. Only God knows, if you believe in God. So I'm claiming that if we want a contract to be stable, viable, to be sustained, the contract must be coalitionally based and incentive compatible and not individual one. Because you want to exclude the coalition formation because the coalition formation can cheat the complementary coalition and make all members of the coalition better off. Okay? So I'm going to insist on coalitional incentive compatibility and not individual. So the incentive compatibility that I gave in the beginning should be a coalitional version if you want stability on the contract, because this contract is not stable. It's not. I mean, any intelligent people will figure out that, come on, I mean, we can do better here. And they will. And you want to eliminate those cases. Finally, I'm going to give you one more example. Oh my God, I have exhausted my time pretty much. I go very slowly. This contract, I'm giving you now a contract. Oh, this is, okay. This is the concept, the private code, which is consistent with all those properties except second best efficiency. And let me tell you what happens in this contract. There are 3 individuals, and the third guy has no initial endowment but has very good fine information. It turns out that concepts like rational expectancy equilibrium or Walrasian expectancy equilibrium cannot even capture this individual. He's a dummy, has 0 budget constraint because he has 0 initial endowments, so he will play, basically he will maximize his expected utility subject to 0 budget constraint. He's going to get always 0. He's excluded, plays no role. And here is a person who can make a Pareto improvement, a kind of an efficient redistribution of the resources and make everybody better off. Agent 3. I think the computer did this because I see all the 3s have become 2 here. This is supposedly 3 again. Okay, so what else we have proofread more carefully? So here it is. Again, this guy doesn't care if it's A or B as before. This guy is C. This guy cares if C occurs, is going to die. This guy is going to die in state B. And here comes agent 3, and he plays the role of the intermediary. In other words, in the good states, agent 1, if state or B occurs, gives 1 unit to agent 3 in state, say, A or B. If state B occurs, if state A and C, agent 2 gives 1 unit. So if state A occurs, 1 unit he took from this guy and 1 unit from the second guy, he keeps them, he has 2, and those guys have 4. Now, when A occurs, the 1 unit he took from this guy, that's why he has 4, he gives this to the other guy. And if C occurs, the 1 unit that took from him, the 1 unit, he gives the first guy. But if state A occurs, he keeps the 1 unit from both guys. It plays the role of intermediary. This is an insurance contract. It's the premium you pay in case you have an accident, right? You pay a premium in the good states, you get something in return in the bad states. And it turns out that this contract is incentive compatible because this guy, agent 3, is the only guy who can cheat the other people. And if A occurs, this guy doesn't know if it is A or B, the other guy doesn't know if it is A or C, but has no incentive to tell them anything else but A, because that's the only state he gets something. Also, the role of information here matters because if I give him the trivial partition like this, he gets 0. I have now rigorous definitions, and on the other screen here, let's see, on this screen here, I was planning to show you how you implement something, and this contract I can implement as a perfect Bayesian equilibrium. This is the game 3. Because I see I'm running out of time, what I want to tell you, you go in extensive form, nature picks a state, and agents move sequentially, and you see the dynamics of the contract, and something which is Bayesian incentive compatible, you see you have gone to 4-4-2 from state A. From state B, you go to 4-1-0, as we have here, for state B, 4-1-0, and state C, you go 1-4-0, here, 1-4-0. And you play perfect Bayesian equilibrium in this extensive form graph. It turns out this is an open question, and it's very important for people who are doing kind of applied mathematics and computer science information, who haven't been able here to go beyond 3 agents. And despite the fact there's a pattern, to develop graphs for more than 3 agents becomes a bit complicated, and you need some kind of algorithmic type of ways to produce this and to compute. It seems to me, because implicit on this is some kind of a fixed point, one should be able to produce kind of generalization of scarf type of algorithms or Merrill and for this type of contracts, because the graph computes. When you play the perfect Bayesian equilibrium, you go into the outcomes and should hold with general preferences and arbitrary utility functions. There is a pattern. I don't have the time to go there, but there is a real distinct pattern there when information sets are compatible and incompatible, where there are common events and non-common events. And you proceed with this compatibility, and my conjecture is that there is a theorem which not only is going to be computable because you have finitely many agents, contracts written by finitely many agents, but also could be a mathematical breakthrough as well. Okay. Let me go back and start summarizing now the last 2 minutes that left. It turns out that the classical notions, like the rational expectations equilibrium that we are still using, do not provide contracts which have any of the desirable properties we want the contract to have. It's just amazing that people keep using the same equilibrium notions which do not have the properties that we want our contract to have. If you want to have a good contract, you have to go into the second best. The private core seems to work, and there is also new work on variations, actually modifications of the Walrasian expectancy equilibrium which work. It's a Bayesian Walrasian equilibrium, and by Bayesian Walrasian equilibrium I mean the following, that each individual, you see let me go back, where the rational expectation equilibrium goes wrong. The rational expectation equilibrium says the following, that agents, can give you the definition, the precise definition. The rational expectancy equilibrium says that agents maximize conditional expect utility. Here is a conditional expect utility, but this is the event, this is the condition on the information the equilibrium price is generated join their private information. In other words, when I maximize my interim utility, I condition myself on the correct conjecture of the equilibrium price. I have conjecture what's the equilibrium price, and I add my private information. This is too extreme. This means that I have this kind of gut-type knowledge to predict the exact equilibrium outcome, and it doesn't seem to work. What works actually is that I can make a Bayesian estimate, I can have a price estimate as to what, based on my own information, what I think the equilibrium price would be, and based on my own price estimate, I have an estimate budget set, and I maximize my interim expect utility conditional on my projected or estimate budget set. So this seems to work and solve the problems of the classical rational expectation equilibrium. The private core works perfectly fine and gives second best Pareto optimal, efficient outcomes, individually rational, set compatible in the coalitional sense, is implemented as a perfect Bayesian equilibrium and extensive form game as you see. And to close, perfect competition can allow you to recover full optimality by formulating precisely negligible information. One thing which is important here is that the measurability characterizes central compatibility, something I didn't give you, and it turns out that this type of work may have impact on what is intellectual property. Intellectual property can be formulated in terms of partitions, and also the measurability can be interpreted as verifiability of contracts. Contracts which are verifiable. You only make contracts which are verifiable because then those verifiable contracts could be self-enforcing, and at the end despite the fact we haven't reached a fully Pareto optimal, we have reached a very good outcome for all the members. The truth is that those contracts could be also decentralizable. That's what we have shown too. We can decentralize by means of prices to those contracts. Okay, by this we're 2 minutes over the time, and I'll stop. I'll ask any questions, and I can thank you for coming. Yeah.
Remember that he is trying to escape the storm, winter storm.
Thank you.